All right, so the first thing we talk about is inverse function of the natural log function, ln of x. And we know this, the inverse of ln of x is e to the x. So these are inverses of each other. Y equals e to the x and x equals natural log of x are inverses of each other, which we know that just from logarithms and rewriting them. You know, the base becomes the base of the log, the exponent is the answer, and the answer from the first one is the letter that gets put here. So this is just basically rewriting. It's just that you need to know the natural log base is e. And so those are inverses of each other. So this is nothing new. We have used this like when we did PERT in pre-calculus, right? E to the RT, something like that. We use natural logarithms to get it out of the exponent, which is the first thing they actually talk about solving these. So solving these are really easy. If you have your variable in your exponent position, the reason you use a logarithm is to get it out of the exponent position. If you log it with the same base, it will get rid of the base of the exponent. So for this one, I would just do the natural log of both sides here. And so on the left-hand side, you will have the natural log of 7. And on the right-hand side, the natural log and the e cancel each other out, and you will just have that x plus 1. And so to solve for x is rather simple. X is going to equal the natural log of 7 minus 1. Remember, natural log of 7 is an actual number. So you put that into your calculator. They rounded to the nearest thousandths. So 0.946 is what they got for x here. So example 2 is just kind of the reverse of that. Example 2 has a natural log, and we have a variable inside there that we need to get rid of. And so we are going to use base e then to get rid of this natural log. And so I do base e of both sides. On the left-hand side, my e and my natural log will cancel out, and I will be left with 2x minus 3. And on the right-hand side, I have e to the 5th. E to the 5th is just a number, so we can solve then for x by adding 3, and then by dividing by 2. And so, once again, this is really a pre-calculus concept. When you put that into your calculator, rounding again to the thousandths place, 75.707. So the first thing I want to look at is properties. Really, base e works like any other base. If you multiply bases, you add their exponents. If you divide bases, you subtract their exponents. The domain is negative infinity to positive infinity. The range is 0 to infinity. You can't take 2.17 to a power and make it less than 0. The function e to the x is continuous, increasing in 1 to 1. The graph of e to the x is concave up in its whole domain. And then as it approaches negative infinity, it is 0. As it approaches positive infinity, it is infinity. And so they give you a picture of the actual graph there. All right, so this is the graph. It's 1 to 1, which means it's going to have an inverse. Natural log is the inverse. Goes towards 0 on the left-hand side, infinity on the right-hand side. So that's what the graph looks like for your e to the x function, natural number function. All right, so let's look at derivatives then. The derivative of e to the x is really simple. It's e to the x. Derivative of e to the x is e to the x. Now, here's the caveat. That is only if x is your exponent. If you have a function as your exponent, say 2x or x squared or 2x plus 3, you then have to also consider the derivative of the exponent. So think of it as the chain rule. If the derivative of e to the x is just e to the x, if we have something in that x position, then we have to do e to the x and derivative of x. If it's e to the u, meaning a function, e to the u times the inside, which would be the derivative of the exponent, du dx. So let's look at one of these. Derivative then of e to the 2x minus 1. You're going to start with exactly what the function is, e to the 2x minus 1. That's the first step. And then you multiply that by the derivative of that exponent. What is the derivative of 2x minus 1? 2. So this derivative is going to look like this, 2e to the 2x minus 1. If you take the next one, e to the negative 3 over x, e to the negative 3 over x. That's going to be part of the derivative, and then we need the derivative of the inside. So the inside I would likely rewrite so I could see it really easily. Multiply and then divide. Multiply negative 3 times your negative 1, right? Which is positive 3. And then you subtract 1 from your exponent. So if I do, my rule here is exponent times my coefficient, that gives me positive 3, and then x, subtract 1 here to the negative 2. So then this derivative will be 3 over x squared. And of course you can just rewrite it 3 e to the negative 3 over x squared. You just repeat the function, then take the derivative of the exponent and multiply it by that. Relative extreme. Relative extreme just means finding a max or min, right? Relative extremes happen at critical numbers. Critical numbers happen where my first derivative is 0, okay? So I need to take the first derivative of this. Now I want to point out this is x times e to the x. X times e to the x, which means you have to use the product rule here. Derivative of the first times the second plus the first derivative of the second, all right? So the derivative of x then, derivative of the first is just 1 times the second e to the x plus the first x derivative of the second. Well, the derivative of e to the x is just e to the x. Derivative of x is just 1, so I don't even have to consider the chain rule here. And so this is my derivative, and I need to set it equal to 0. Equal to 0. Now, when you have something equal to 0, the first way you're going to look to see if you can solve this is by factoring. So is there anything I can factor out of these that is in common? What's in common to those two groups? Yes, e to the x. E to the x, I'm left with 1 plus x. All right. Now, the question would be, when does e to the x equals 0? Well, e is like 2.17 blah, 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 never-ending number. What power could I take it to make it equal to 0? Yeah, it never equals 0, ever. So this will never equal 0. So then I just have to consider this. So when does this equal 0? Well, this equals 0 at -1 and -1. So I know I will have a relative extreme at -1. Now, if I want my y value here, -1, and then whatever my y value is, I just plug it in here. -1 times e to the -1, that's -1 over e. And they just left it -e to the -1, but that's probably a little more proper. All right, so if they wanted to know what the y value is, you would just plug it back in. So this here is the product rule. Remember f and g, derivative of f times g plus f, derivative of g. This is f, this part is g. Number y, so they're denoting y as medical doctors in thousands in the United States from 1980 to 1997 can be modeled. And they give us this exponential function here with your natural number. Or t equals 0 represents 1980. At what rate was the number of MDs changing in 1992? All right, so at what rate something is changing, that is always derivative. At what rate something is changing, we are looking at derivative. All right, so if y is the number of doctors and they want when the number of doctors is changing, we need to find y prime, right? And so for us to find y prime, we are going to take the derivative of this. This is simply e to a power. It has a coefficient. That's okay. The coefficient for it just stays there. So we're going to say, well, the derivative is going to be this, 475, 520, e to the 0.0271 t, right? E to the t. And then we take the derivative of the exponent here and multiply it by that. Well, the derivative of that exponent is just the coefficient. So just times 0.0271. All right. So we did the function itself, that's the derivative, times the derivative of the exponent. That's my total derivative, right? If I have e to the u, my derivative is e to the u times the derivative of u. And that's what I did. Okay? So the derivative of e to the 2x was e to the 2x times the derivative of 2x. There we go.
So it's not the normal derivative.
So even though it has the number in front of it.
If it had been like 3e to the 2x, it would have been 3e to the 2x times 2.
Oh, so that doesn't count as a number in front of it.
The number in front of it is just a number in front of it. Like it's just like a coefficient. Like if you had the derivative of 3x squared, all you do is multiply the derivative by the 3. So that's all you do.
Okay.
You just multiply the derivative by that big number there. Now when you multiply these two numbers, that's where they got the 12,887. E to the 0.0271 t. They just multiplied the 475, 520, and the 0.02. So this is where they got their final answer for y prime. All right, y prime. Now, that's my derivative. So that's where I could find instantaneous rate of change. All right, instantaneous rate of change is first derivative. They want the instantaneous rate of change at 1992. If 1980 is 0, what number then is 1992? 12. So if I want to find 1992, I'm going to put a 12 in for this t and calculate at what rate the number of doctors was changing. So I'll really it's just all numbers times e to the 0.0271 times 12, right? And they rounded to the nearest doctor because we don't have part of a doctor, right? 17,839 doctors per year. So for this one, the derivative is the function that they gave you, and then the derivative of the exponent. So I just did over here the derivative of the exponent. I rewrote square root of x as x to the 1/2. Then just take the derivative, multiply by 1/2 and subtract 1. 1/2 minus 1 is negative 1/2. So I got, that should be negative. That should be, so yeah, I've dropped it here as a negative. There we go. So I just put my 2 in my denominator. My negative 1/2 drops to the denominator because it's negative, and 1/2 is just square root. So I said the original function times the derivative of the exponent. That's those two. And this is just the simplification. This is the numerator, this is the denominator. If I were to do the natural log of x squared and I wanted that derivative, it would be 2x over x squared, and then simplify it. Derivative of what's inside over what's inside. All right? So for this one, if I want the derivative of this, I want the derivative of the inside over the inside, okay? So the denominator here is kind of easy, right? Denominator here is just this guy. All right, but then I have to take the derivative of this, okay? Yes? So far, so good. The derivative of the 1, that is just what? Plus the derivative of e to the 2x. Well, that is e to the 2x times 2, right? So I have 2e to the 2x over 1 plus e to the 2x, right? So it looks daunting, but really it's not. That would be your answer. Derivative of the inside, that's 0 plus your e to the 2x times 2 over the inside, 1 over e to the 2x. And you're done. All right, so integration really is just simple. If the derivative of e to the x is e to the x, then the antiderivative of e to the x is also e to the x, right? If the derivative of e to some function is just e to the function times the derivative of the function, then the only thing I have to consider is what is inside that function that I need to maybe take out of with a u substitution, all right? So really going back and forth, I think e to the x is a really easy derivative and antiderivative. Let's look at this first one. So if I have e to the u, my u here would be the 3x plus 1. I know that my derivative would have considered the derivative of 3x plus 1. So if I do u substitution, u would be my 3x plus 1. du would be 3 dx. I don't have a 3 there, right? There's no 3 in my problem outside of the exponent. So 1/3 du would be my dx, okay? So I don't have to rewrite this if I don't need to. I just need to know that in my answer, I'm gonna have 1/3 to take care of that 3. So if my derivative of this would have been e to 3x plus 1 times 3, my antiderivative of this is just going to be the e to the 3x plus 1 times 1/3, or e to the 3x plus 1 over 3 plus c, because it is indefinite integration. Let's look at this one. Basically, my function here is the e to the negative 2x, negative x squared. So my function that I'm looking at is this guy, right? Which means I need to consider a u of negative x to the second power. Well, du would be negative 2x dx. What do I have? I have a 5x dx. So I would have to multiply both sides by negative 5/2 to make that negative 2 a positive 5, right? So that just means my final answer is going to have this guy in it, negative 5/2. So my answer is going to be negative 5/2 times my function that I talked about here, e to the negative x squared, all right? And then if I want to simplify that, I can. You don't necessarily have to. if you really simplified this, you would actually put that e to the negative x squared on bottom, right? It's to the negative.
So you can just leave it like that.
But you do have to remember this is indefinite integration. So they left it like this, but you have to remember him. This is indefinite. We do not have a top and bottom at this point for boundaries. All right. So my function that I'm looking at then is e to the 1/2 at 1 over x, e to the 1 over x. So when I do like a u substitution here, I need to consider u equal to 1 over x, or x to the negative 1, right? So du then, we would multiply by negative 1 and subtract, or negative 1 over x squared, right? I technically have a positive 1 over x squared, right? So my answer is just going to have to get rid of this negative 1, which means I would be multiplying my answer by a negative 1. So it's just going to be negative 1 times my function that I was talking about, e to the 1 over x. So negative e to the 1 over x plus c. That would be my derivative, my antiderivative here. So you can do full u substitution if you want to, or you can just write it out to see what would happen if I did it, right? Is there anything I need to take care of? Look at the next one. My function I'm talking about is e to the cosine of x. So when I do a u substitution, I would need to consider just the cosine of x. What's the derivative of the cosine of x? Negative sine of x. What do I have? Positive sine of x. So I just need to multiply by negative 1. So my final answer is going to be my function times that negative 1. Negative 1 times the times e to the cosine of x plus c. So just negative e to the cosine of x plus c. All right, this has been indefinite integration plus c plus c plus c because I don't have boundaries, right? So integration works exactly the same. You integrate and then you just plug in your numbers. All right, let's look at this one, e to the negative x. What am I going to have in front of my answer when I take this integration? Probably a negative 1 because the derivative of negative x is negative 1 and I don't have a negative 1, right? So my integration here is going to be negative e to the negative x from 0 to 1. So when I plug that in, negative e to the negative 1 minus negative e to the 0. And you plug it in. So it would just be, I mean, this is just going to be 1 plus 1. So you end up with negative 1 over e plus 1.
Do you get the pros by doing?
Yeah, so you look at that negative x and determine if there's something that's going to be needed to do. Now, when you plug that in, you get an actual number here, right? E is just a number. So when you plug that in, you get 0.632. Let's look at this next one. The function here that I'm looking at is this 1 plus e to the x, but it is on the bottom. It is on the bottom. So remember the antiderivative of something in the denominator to the first power, which is what this is, right? This is in the denominator to the first power, that group. When I take that antiderivative of something in the denominator, like 1 over x, right? If I did that derivative, make that x a little prettier. If I did this antiderivative, it equals natural log of x, right? So I have this in the denominator here. So I am definitely going to have the natural log of 1 plus e to the x. I have to consider the derivative of that. What is the derivative of 1 plus e to the x? 0 plus e to the x. So I have my derivative taken care of. There is nothing to consider on u substitution here. All right, natural log of 1 plus e to the x is my derivative, right? And I am just going from 0 to 1. So I'm going to have the natural log of 1 plus e to the 1 minus the natural log of 1 plus e to the 0. All right, e to the 0 is just 1. All right, natural log of 1 is just 0. So if you plug this into your calculator, you will get, again, approximately rounded to the nearest thousandths place, something that looks like that. All right, the last one. The function that I'm actually going to look at here is cosine of e to the x. Cosine of e to the x, right? Now, cosine has an antiderivative. What is the antiderivative of cosine? Just sine, right? Antiderivative of cosine is just sine, right? So all I have to consider is this inside guy, right? Use substitution there. What is the derivative then of e to the x? Because I have to consider it. It's just e to the x. It's already taken care of, right? It's right there. So my antiderivative here is just my antiderivative of my cosine, sine of e to the x. When I take this derivative, I would get cosine e to the x times e to the x. That's what I would get. And I'm going from -1 to 0. So I would have sine of e to the 0 minus sine of e to the -1. All right, and that again is in actual numbers. E to the 0 is just 1. But when you plug that in, 0.482. Those are actual numbers. So here's the deal. If I were to take the derivative of this, I should get that, right? If I were to take the derivative of this, I should get this. And if I were to take the derivative of this, I should get that.